DeepSeek-V4 just dropped a landmark open-source AI model. It delivers highly efficient million-token context, significantly advancing long-context intelligence. Let's start with today's featured paper, DeepSeek-V4, Towards Highly Efficient Million-Token Context Intelligence, by DeepSeek AI from DeepSeek AI. This paper introduces a flagship open-source model family that significantly advances the state-of-the-art in long-context processing through a novel hybrid attention architecture, representing a landmark release that will be widely used and benchmarked against. Here's a full breakdown.
First, let's look at the core of the hybrid attention, which combines two types of information. It merges local context from the sliding window KV entries with globally important context from the selected compressed KV entries, right here at the concatenation block, feeding into the model's layers. The architecture also uses a novel connection method to improve how information flows, enhancing the standard residual pathways. This technique is a key reason for the model's strong performance, but it's a broader architectural feature not detailed in this specific attention diagram. Next, to train this entire system, a custom optimizer was developed to make the model learn both faster and more reliably. This optimizer is part of the training process, which happens before we get to the inference time data flow shown here. DeepSeek-V4 Pro Max demonstrates strong performance, notably achieving 90.2 on Apex shortlist and the highest rating of 3,206 on Codeforces, outperforming Claude, Opus 4.6, Max, and GPT 5.4x high. While competitive on SW-verified, DeepSeek-V4 Pro Max is surpassed by Gemini 3.1 Pro, high on Simple QA verified in Tulithlon, and by GPT 5.4x high on Terminal Bench 2.0.
That was our featured paper. Today, ArXiv received 663 new computer science papers across 55 subfields. Let's look at the research landscape before we continue with the remaining papers. Today's AI research landscape is buzzing, especially with deep dives into LLM behavior and the exciting advancements in multimodal AI, alongside a strong focus on trustworthy systems. Now, let's see which papers stood out. Prepare for a surprise. AI backdoors can be triggered by tiny floating-point math differences across platforms. Also, passive human videos might actually outperform costly robot data for training embodied agents. Now, let's explore each of today's trends in detail, starting with number 1.
Trend 1 of 10. Data, features, and model selection. This trend explores the critical interplay of data, feature engineering, and model selection for robust and efficient machine learning systems. This cluster covers 36 papers. Representative work includes sign language datasets at scale, a comprehensive survey on resources, benchmarks, and annotation standards, calibrating generative models to feature distributions with MMD fine-tuning, and exploring feature extraction technique parameters for acoustic gunshot classification. Trend 2 of 10. Advanced speech and audio processing. This trend explores cutting-edge techniques in speech and audio processing, encompassing representation learning, synthesis, recognition, quality assessment, and deepfake detection. This cluster covers 26 papers. Representative work includes improving code-switching ASR with code-mixing guided synthetic speech, SGEPA, soft clustering anchors for self-supervised speech representation learning, and FlowFake, liquid networks for audio deepfake detection. Trend 3 of 10. Large language model behavior and bias. This trend examines large language model behavior, including biases, failures, and generalization across diverse tasks and applications. This cluster covers 112 papers. Representative work includes exposing the unsaid, visualizing hidden LLM bias through stochastic path aggregation, ensembles of large language models for identifying EQ, 5D studies in PubMed based on their abstracts, and disentangling linguistic relatedness from task alignment in cross-lingual transfer. Trend 4 of 10. Abstract mathematical and theoretical concepts. This trend explores foundational mathematical structures, theoretical frameworks, and abstract concepts across diverse scientific and computational disciplines. This cluster covers 77 papers. Representative work includes computational identifiability, an alternative way of defining finite graphs, and on epimorphisms of hypergraphic automata and input symbol semigroups. Trend 5 of 10. Multimodal AI and advanced reasoning. This trend explores integrating diverse data modalities with sophisticated reasoning techniques, to enhance AI understanding and problem-solving. This cluster covers 54 papers. Representative work includes DeepSeek-V4 towards highly efficient million-token context intelligence. Does text actually help? Uncovering and resolving text collapse in multimodal time series forecasting and concept flow models. Anchoring concept-based reasoning with hierarchical bottlenecks. Trend 6 of 10. Trustworthy, robust, and efficient AI. This trend explores methods to build AI systems that are reliable, resilient, and computationally efficient for various applications. This cluster covers 60 papers. Representative work includes granularity-regulated adaptive computational efficiency for optimal verification in test time scaling. When to trust, how to distill. Multi-foundation model guidance for lightweight, robust scientific time series forecasting, and CPM. Continual AI-assisted pace mapping with active learning. Trend 7 of 10. 3D generative models and scene understanding. This trend explores advanced computational methods for creating and interpreting three-dimensional environments and objects. This cluster covers 83 papers. Representative work includes performance analysis and optimization of 3D generative diffusion models across GPU architectures. ProMuse, progressive multimodal uncertainty-guided staged evidential Alzheimer's disease classification, and 3D scene graphs. Open challenges and future directions. Trend 8 of 10. Multi-agent systems and trust. Investigates multi-agent systems, addressing challenges of trust, reliability, and robust coordination for effective operation. This cluster covers 80 papers. Representative work includes supporting design decisions in rule-based model transformations, trustworthy multi-agent systems, mitigating semantic drift with the ARGent signaling protocol, and agent armor, a framework, evaluation, and mitigation of coding agent failures. Trend 9 of 10. Autonomous robot learning and control. This trend focuses on developing advanced learning and control methods for robots to achieve robust and human-like autonomy in complex tasks. This cluster covers 58 papers. Representative work includes Physical Atari, a robust and accessible platform for real-time reinforcement learning on robots. Work Benchmark, a Lego-based assembly benchmark with an assembly-by-disassembly baseline for the Smart Manufacturing League, and human-like autonomy emerges from self-play and a pinch of human data. Trend 10 of 10. Learning model structure and parameters. This trend explores methods for automatically determining both the architecture and internal values of computational models. This cluster covers 77 papers. Representative work includes information lattice learning as probabilistic graphical model structure learning, Weibull weight scale parameter evolution under Adam W. training dynamics, and neural architectures as functional priors in physics-informed control problems.
That's the full research landscape for today. Remember, our number 1 paper, DeepSeek-V4, towards highly efficient million-token context intelligence, was already covered at the top. Now, let's continue with papers 2 through 10 one by one. Up next, our second paper out of 10, FloatDoor. Platform-triggered backdoors and LLMs by Nils Luce and Thomas Eisenbarth from University of Lübeck. This paper uncovers a brilliant and deeply concerning new attack vector, where backdoors and AI models are triggered by subtle, platform-specific differences in floating-point math, fundamentally challenging our assumptions about model deployment security. Let's break down its key contributions.
Let's start by looking at panel C, which visualizes our fingerprinting method. The heat map shows the relative change in hidden states across different layers on the x-axis, with a strong, bright orange signal in the later layers indicates a significant, input-independent change. Feeding into this, our first step uses a trigger adapter to create a platform signature, as shown in panel B. This adapter amplifies the tiny numerical differences between platforms, which you can see as the strong orange band appearing in the middle to late layers. Next, a second adapter binds this platform signature to a malicious behavior, which we can see in panel D. This plot shows the cosine similarity between the change in the hidden state and a target direction, with a strong blue region shows the hidden states being consistently pushed in a specific direction. The table evaluates different methods on CPRSD losses, probe margin and accuracy, and changes in utility on MMLU and HelloSwag benchmarks. The S methods generally achieve lower CPRSD losses and maintain utility on MMLU and HelloSwag better than the M methods. which shows substantial drops in performance on these benchmarks.
Up next, our third paper out of 10, HumanScale. Egocentric human video can outperform real robot data for embodied pretraining by Junsheng Ma and Duomin Wang. This paper makes a field-shaping, contrarian claim that passive human videos can be more effective for pre-training embodied agents than expensive, actively collected robot data, potentially solving the primary data bottleneck in robotics. Let's break down its key contributions.
Our process begins by sourcing massive amounts of egocentric human video, which provides a rich, open-world diversity of interactions. This raw data forms the foundation for teaching our model a general understanding of the physical world. This video data is then used to pre-train our World Action Model, or WAM. The model learns to connect text instructions and visual observations to predict future states and generate corresponding actions. Finally, we perform a post-training step using a small amount of real robot data. This crucial adaptation phase fine-tunes the model, aligning its general world knowledge with the specific embodiment and action space of the robot. Our egocentric method achieves a substantially higher in-distribution performance of 92.5% compared to the 2.2 baseline's 40%. Furthermore, it demonstrates strong generalization with 90% out-of-distribution performance, whereas the baseline shows 0%.
Up next, our fourth paper out of 10, Your Mouse and Eyes Secretly Leak Your Preference. LLM alignment using implicit feedback from users by Haoxuan Chong and Haim Zamani from University of Massachusetts, Amherst, USA. By proposing to use implicit user signals like mouse and eye movements for alignment, this paper offers a brilliantly practical and scalable solution to the massive data bottleneck in collecting human preference feedback for LLMs. Let's break down its key contributions.
First, we have users interact with a chat interface, where they read responses from a large language model. As they do this, we collect their implicit feedback by tracking both their eye-gazing trajectory and their mouse trajectory. Feeding into this process, we gather data from many different users to create our new IFLLM dataset. This dataset pairs the LLM's text responses with the corresponding implicit feedback signals we collected. Next, after performing feature extraction on the raw trajectory data, we use it to train our reward model. This model, based on a random forest, learns to predict user preferences directly from their implicit feedback. Finally, the preferences predicted by our implicit feedback model are used to improve the LLM itself through a process called LLM alignment. We specifically use RDPO to fine-tune the model, making its future responses better aligned with user preferences. The implicit feedback methods, particularly RF+, IF-gaze, and RF+, frequently achieve the highest overall scores and win rates across various language models. This approach often outperforms baselines like explicit feedback and modern BERT plus text, for example, reaching an overall score of 4.91 and a win rate of 0.593 for OLM021B.
Up next, our fifth paper out of 10, Apparent Psychological Profiles of Large Language Models Are Largely a Measurement Artifact by Yelena Meyer and Dirk Wolf from Max Planck Institute for Human Development. This paper delivers a landmark methodological critique, using a formal psychometric framework to convincingly argue that assigning psychological profiles to LLMs is largely a measurement artifact, forcing a necessary course correction for the field. Let's break down its key contributions.
Let's start by looking at the model, which separates the psychological construct from how a response is generated. The key insight here is that in addition to the actual trait like neuroticism, there's a separate response bias that pushes the answer one way or another, like a preference for low values on a scale. Feeding into this, the research found that this response bias isn't static across different models. While the bias tends to get smaller as models become more capable, it never completely goes away, even in the most advanced systems. Next, to counteract this, the paper introduces a design principle called response orthogonality to build better measurement tools. This is shown in the measurement section, where for some items the trait and bias align, but for others they are set up to be orthogonal, pulling the response in opposite directions. Finally, this leads to a striking conclusion about an LLM's apparent psychological profile. By carefully selecting only forward items or only reverse items from the measurement design, you can significantly alter or even manufacture a specific personality. Large language models, LLMs, are significantly more sensitive to the proportion of reversed keyed items in psychological scales compared to humans. Specifically, LLMs show a strong negative Pearson correlation of approximately -0.9 between reversed items and inter-item correlation, whereas humans exhibit a weaker negative correlation of about -0.4.
Up next, our sixth paper out of 10, FAPO, Fully Autonomous Prompt Optimization of Multi-Step LLM Pipelines by Paul Kasyanek and Amin Karbasi from Foundation AI, Cisco Systems Incorporated. This paper introduces a powerful new paradigm of autonomous, model-driven optimization for complex LLM pipelines, representing a significant step towards self-improving AI systems. Let's break down its key contributions.
Looking at our results table, the FAPO column shows the performance of our new framework across several benchmarks. You'll notice it consistently achieves high scores, demonstrating its effectiveness in optimizing these complex pipelines. Feeding into this, FAPO's strength lies in its iterative evaluation, which is especially clear on challenging benchmarks like Hover. Here, our framework diagnoses deep-seated issues, resulting in massive performance boosts that push scores from the 20s and 30s into the 80s. Next, FAPO's adaptive optimization strategy is at work, where it intelligently edits and Contribution 4. When prompt optimization proves insufficient, the system escalates to structural changes within permitted scopes. This mechanism addresses deeper architectural bottlenecks identified through attribution. This image describes the components and roles within the FAPO system, including agents for optimization and evaluation commands. However, it does not present any performance metrics, benchmarks, or comparisons to prior work or baselines.
Up next, our seventh paper out of 10. Current world models lack a persistent state core by Jinpeng Liu and Jie Chao from University of Science and Technology of China. This paper makes a fundamental conceptual critique that could reorient the entire field of world models by highlighting the critical, overlooked need for a persistent state decoupled from observation. Let's break down its key contributions.
On the right, we introduce our new benchmark, the WR-Bench metric, which is designed to systematically test world models. It takes the generated video sequence as its input for evaluation. Feeding into this, we see how camera motion is treated as a deliberate action, creating a path where the camera can go away from subject and return later. This sequence of views is what the model must process to maintain a persistent world state. Next, the WR-Bench metric itself is a comprehensive evaluation chain using several powerful models. It employs components like Quinn, Dino, and VGGT to check different facets of the generated video. Finally, this chain performs a multi-stage assessment, checking for things like camera precision, visual integrity, and crucially, consistency when the subject returns to view. For example, Quinn 3.5 is used to check for both visible and return spatial/state consistency. Models under the model-inferred condition, such as WanFun 2.2, A14B, demonstrate strong average performance, generally outperforming models in the geometry cache and prompt-only categories. However, the highest overall average score of 0.729 is achieved by InSpatio World 14B from the source video condition.
Up next, our eighth paper out of 10, Scaling Self-Play for End-to-End Driving by Luke Rowe and Liam Paul from Mila. This work demonstrates a potential paradigm shift in autonomous driving by successfully scaling self-play in simulation, directly challenging the prevailing and costly wisdom of relying on offline human demonstration data. Let's break down its key contributions.
First, our gigapixel simulator takes a vectorized state S and uses a batched render to create multiple pixel-based observations in parallel. This high-throughput approach allows us to efficiently generate training data, like these pixel views for I equals 1 to n, directly from a simulation. Feeding into this, we use a self-play dagger approach where a privileged Pi_score teacher generates expert trajectories from a full-state rollout. A Pi_score student then learns from these trajectories using only pixel observations, with all data collected in the replay buffer for training. Next, to make our policy work in the real world, we introduce a lightweight perception adaptation step. This involved aligning the features from a simulation perception module, F_per_sim, with a real-world one, F_per_real, using a perception loss LPerc to bridge the sim-to-real gap. The DrivOR method, particularly its variant with HumanScale, achieves the highest per-stage score, reaching 84.2 for Stage 1 and 64.6 for Stage 2. This performance substantially outperforms other DrivOR variants and prior methods like ZTRS or GuideFlow on this metric, and also leads in the EPDMS score.
Up next, our 9th paper out of 10, Argus. Production scale tracing and performance diagnosis for over 10,000 GPU clusters by Jiaxing Zhou and Qi Zhang from Tencent. This paper provides a critical and production-validated systems solution to the urgent, high-cost problem of performance debugging in the massive GPU clusters that power modern AI. Let's break down its key contributions.
Our system, Argus, starts with the trace producer, which gathers detailed observations from multiple levels of the training process. This includes everything from the high-level CPU stack and framework semantics down to the individual GPU kernels. Feeding into our unified data pipeline, the raw traces are then handled by the processor. This pipeline efficiently collects, filters, and compresses the data before a real-time upload to storage, which is key to making always-on tracing practical. Next, our progressive diagnosis framework, shown in the analysis section, takes this process data. It moves through a series of steps, starting with iteration anomaly detection and continuing through straggler attribution and kernel inspection to pinpoint performance issues. Argus demonstrates comprehensive capabilities, achieving low overhead, fine granularity, always-on operation, and continuous real-time analysis, unlike many prior systems such as Greyhound, C4, and Megascale, which often lack fine granularity. Furthermore, Argus provides strong diagnostic capabilities, including fail-slow localization and performance optimization, outperforming most other methods like Holmes and Minder that lack performance optimization.
Up next, our 10th paper out of 10, Configurable Clinical Information Extraction with Agentic RAG, What Works, What Breaks, and Why by Marie Bauer and Jens Klesik from Introduction. This work reports on a real-world, on-premise deployment of an agentic AI system in a complex clinical setting, providing invaluable, credible insights that bridge the gap between research and high-stakes practice. Let's break down its key contributions.
Here we have the core of the system, the extraction agent, which is designed to pull specific information based on a clinician-defined extraction schema. This agentic pipeline forms the foundational architecture for processing complex patient data. Feeding into this agent is the complete patient context, which integrates a huge amount of information. This includes unstructured documents, retrieval chunks, and structured data like labs and medications from various hospital systems. Next, the agent's output is a grounded answer, which contains the extracted value. Crucially, it also includes the cited sources, allowing a clinician to easily verify the information before making a decision to accept or reject it. This table details the accuracy and empty percentages for various field types extracted by the agentic RAG method. However, the provided image does not include information for comparison against prior work or other baselines.
That's all for today's ArXiv Computer Science Daily. If you found this helpful, please leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.